Tonight, we're going to confront the most disturbing question in the history of science. Not because the question is hard to ask, because every answer we come up with is worse than the one before it. We have been scanning the sky for signals from other civilizations for over 60 years. We have pointed our most powerful telescopes at hundreds of thousands of stars. We have listened across billions of radio frequencies. We have built systems so sensitive they could detect the equivalent of a cell phone signal from the far side of the solar system. We have searched with resources, intelligence, and dedication that would have seemed miraculous to scientists of a previous generation. We have found nothing. Not a whisper, not a blip, not a structured signal, not a confirmed artifact. Not a single piece of definitive evidence that anywhere in this vast, ancient, chemically fertile universe, any mind other than ours has ever formed a thought. And that silence is not just strange, it is mathematically impossible, or it should be. The universe is 13.8 billion years old. It contains an estimated 2 trillion galaxies. Our galaxy alone, the Milky Way, which is not particularly large by galactic standards, contains somewhere between 100 and 400 billion stars. Data from NASA's Kepler Space Telescope, which spent 9 years staring at a single patch of sky and cataloguing every dimming event that might indicate a planet crossing in front of a star, revealed that virtually every star in the galaxy has at least one planet. Many have several. When astronomers applied that discovery to the full stellar census of the Milky Way, the number they arrived at was staggering. Conservative estimates. At least 300 billion planets in our galaxy. More optimistic, closer to 1 trillion. Of those planets, a meaningful fraction orbit within what scientists call the habitable zone, the band of orbital distance around a star where temperatures allow liquid water to exist on a planetary surface. Liquid water is the universal prerequisite. Every life form we know of requires it. Current estimates suggest there are between 40 and 60 billion potentially habitable, roughly Earth-sized planets in the Milky Way alone. Now, add time. Many of those worlds orbit stars billions of years older than our Sun. Life appeared on Earth almost immediately after the planet cooled enough to permit it within a few 100 million years of formation. In geological terms, that's essentially instantaneous. If life has the same tendency to arise quickly elsewhere that it demonstrated here, then there have been billions of years of biology happening on billions of worlds in our galaxy before humanity wrote its first word. Somewhere in that arithmetic there should be signals, there should be megastructures, there should be something, anything that breaks the silence. And yet the silence remains. It has a name. Scientists call it the Fermi Paradox. Named for Nobel Prize-winning physicist Enrico Fermi, who in 1950 crystallized the contradiction between the mathematical expectation of abundant life and the observational reality of total silence into a single, devastating question. Where is everybody? 74 years later, we still don't have an answer. Not because we haven't tried, not because the question isn't taken seriously, but because every solution we come up with is terrifying in its own specific way. Some solutions say we are alone in a way that makes the universe meaningless in its emptiness. Some say we are not alone but are in danger from that fact. Some say we are being watched. Some say we are walking, right now, towards something that kills every civilization that reaches our level of capability before it can reach the stars. 9 major solutions. Every single one of them will change how you think about everything you see when you look up at the night sky. Before we begin, if questions like this are the kind that keep you up at night in the best possible way, take a second to like this video or subscribe. It helps this channel reach more curious minds exactly like yours. Now, let's begin. The math that broke everything. The year is 1950. Los Alamos, New Mexico. A cafeteria lunch that will, without any exaggeration, permanently alter how humanity conceives of its place in the cosmos. Enrico Fermi is, by any serious measure, the most practically gifted physicist of the 20th century. The man who designed and built the first functioning nuclear reactor, constructing it in an unused squash court beneath the bleachers of a football stadium at the University of Chicago. The man who helped develop the atomic bomb, a Nobel Prize winner with a particular gift legendary among his peers for arriving at accurate quantitative estimates from almost no information at all. He could calculate the number of piano tuners in Chicago using nothing but logic and a few basic facts about population density, piano ownership, and tuning frequency. During the Trinity nuclear test, while other scientists watched the fireball from miles away, Fermi tore a piece of paper into small fragments, held them at chest height, and released them at the moment of the blast. He watched how far the shockwave displaced them when it arrived. From this simple observation, he estimated the yield of the explosion at 10 kilotons, remarkably close to the measured value of around 20. On this particular day in 1950, Fermi is having lunch with colleagues Herbert York, Emil Konopinski, and Edward Teller. The conversation drifts, as conversations among physicists at Los Alamos in those years often did, into the strange and the speculative. Someone mentions a recent New Yorker cartoon depicting cheerful aliens stealing New York City's public trash cans. The group laughs. The conversation wanders to other things. And then, sometime in the middle of the meal with no particular preamble, no dramatic setup, no sense that he was about to articulate something that would define a scientific field for the next 7 decades, Fermi looks up from his food and asks a question so simple it sounds like the beginning of a joke. But where is everybody? His colleagues understood immediately. The logic was obvious once stated. If the galaxy is as vast and as old as we know it to be, and if the physics and chemistry that produced life on Earth operate by the same universal laws everywhere else, which every observation confirmed, they did then intelligent civilizations should have arisen far earlier than us, millions of years earlier, billions. Even at speeds far below the speed of light, a sufficiently motivated spacefaring civilization could spread across the entire Milky Way in 10 million years or less. That sounds like an incomprehensibly long time. But the galaxy is 10 billion years old. 10 million years is 1/10 of 1% of its age. It is, in cosmic terms, not even a rounding error. And yet no evidence, no structures that shouldn't be there, no signals that couldn't be explained by natural processes, no visitors, no ruins, no footprints in the asteroid belt, nothing. Fermi's question became the definition of a paradox, a situation where seemingly valid premises lead to a conclusion that contradicts observation. The math says the universe should be full. The universe appears to be empty. Something is wrong with either our assumptions or our understanding of what full would look like. In the 74 years since that cafeteria lunch, the paradox has only deepened. Our telescopes have gotten better. Our radio detection systems have become orders of magnitude more sensitive. We have found thousands of exoplanets, confirming that planetary systems are not rare exceptions but the default state of solar formation. We have discovered extremophiles organisms on Earth that thrive in conditions previously thought to be lethal. From the boiling hydrothermal vents of deep ocean floors to the radioactive cooling water of nuclear reactors, expanding our conception of where biology might exist. Every discovery about the ubiquity of the conditions for life has made the silence louder. To understand why scientists take this silence so seriously, you need to understand the instrument through which they try to quantify it. The Drake equation, giving the silence a face. In November 1961, 11 years after Fermi's lunch, a 29-year-old astronomer named Frank Drake convened the first formal scientific conference dedicated to the search for extraterrestrial intelligence. The venue was the National Radio Astronomy Observatory in Green Bank, West Virginia, a facility nestled in a radio-quiet valley, surrounded by mountains, chosen specifically because the surrounding terrain and federal regulation created a zone of electromagnetic silence that allowed its telescopes to hear the faint signals of the distant universe without interference from television, broadcasts, radar systems, or radio stations. 10 people attended the first Green Bank conference. Drake, in addition to organizing it, opened the meeting by writing an equation on a blackboard, an equation not designed to give a precise answer, but to structure the question to identify every factor that would determine how many communicating civilizations existed in the galaxy right now, and to force the scientific community to be explicit about what they knew, what they estimated, and what they were simply guessing. The Drake equation, written symbolically as n equals r star times fp times ne times fl times fi times fc times l. 7 factors, multiplied together, r star, the rate of formation of stars suitable for the development of intelligent life. Drake estimated about 1 star per year. Modern measurements suggest the real number is closer to 3, and the fraction of those that are sun-like, stable, and long-lived enough to support biological evolution is substantial. FP, the fraction of those stars with planetary systems. In 1961, this was completely unknown. Some astronomers thought planetary systems might be rare, perhaps requiring unusual conditions to form. The Kepler Space Telescope's 9 years of observations settled this definitively. Planetary systems are essentially universal. The fraction is close to 1. Nearly every star has planets. NE, the number of planets per solar system with environments suitable for life. Earth is the only confirmed example. But the discovery of the TRAPPIST, one system's 7 planets orbiting an ultracool red dwarf star 40 light-years away, at least 3 of which orbit within the habitable zone, suggests that multiple habitable zone worlds per system are plausible, not exceptional. FL, the fraction of suitable planets on which life actually appears. This is where certainty evaporates. On Earth, life appeared almost immediately after conditions permitted. That suggests it might be common, but we have exactly 1 data point. FI, the fraction of life-bearing planets on which intelligence evolves. Again, 1 data point, Earth. The counter-argument is that multicellular life existed on Earth for hundreds of millions of years before intelligence arose, and there's nothing obviously inevitable about the path from complex organisms to spacefaring minds. FC, the fraction of intelligent civilizations that develop detectable communication technology. This assumes that any species smart enough to develop civilization would eventually discover electromagnetism and use it to communicate. Given that we did it within a century of the relevant physics being understood, this fraction might be relatively high. L, the length of time a civilization actively communicates. This is the most important and most uncertain variable. A civilization that develops radio technology and then destroys itself in nuclear war 50 years later contributes 50 years of signal. A civilization that lasts 1,000,000 years contributes 1,000,000 years. The range of plausible L values spans 12 orders of magnitude, and L is where every version of the Great Filter lives. When Drake filled in the numbers using 1,961 estimates, the equation suggested there should be between 1,000 and 100 million active communicating civilizations in the Milky Way right now. The most optimistic interpretation of the equation, used by Carl Sagan in his television series Cosmos, suggested the number might be in the millions. We have found none, which means either several of the middle terms, the probability of life arising, the probability of intelligence evolving, are so small they approach 0, or L is catastrophically short, or there are factors the equation doesn't account for, or our search methods are so inadequate we've been looking in the wrong place, in the wrong way, for the wrong thing. Each of those possibilities is a different story about the universe, and each story leads somewhere frightening. The 65-year search, how hard we've tried. Before we reach the solutions, you need to understand how seriously and how persistently humanity has looked, because the failure to find anything after this level of effort is not a casual oversight. It is a thundering negative data point that demands explanation. The formal search began in April 1960. Frank Drake, the same Drake who would write the equation 14 months later, pointed the 8-5-foot Howard E. Tatel telescope at the National Radio Astronomy Observatory toward 2 nearby sun-like stars, Epsilon Eridani, about 10.5 light-years from Earth, and Tau Ceti, about 12 light-years away. He chose a frequency of 1,420 MHz, the emission frequency of neutral hydrogen. This was considered the most likely communication channel because hydrogen is the most abundant element in the universe, and any technologically literate civilization capable of building a radio transmitter would know this frequency. Drake named his project Project Ozma, after the queen of the fictional land of Oz, a place that was distant, difficult to reach, and populated by strange and exotic beings. He listened for 2 months, intermittently, using whatever telescope time he could secure between the observatory's other commitments. He heard nothing from either star. Nothing organized. Nothing structured. Nothing that could be distinguished from the random hiss of galactic noise. In the 65 years since Project Ozma, The search has grown from a single astronomer with access to one radio dish into a coordinated international scientific enterprise. The SETI Institute, a non-profit research organization founded in 1984, coordinates and funds SETI research across multiple disciplines and institutions. The Allen Telescope Array in the Cascade Mountains of Northern California, funded by a $30 million donation from Microsoft co-founder Paul Allen, consists of 42 individual radio dishes working in concert as a single large aperture interferometer. It monitors a wide swath of sky simultaneously, looking for narrowband signals, transmissions concentrated in an extremely narrow frequency band, a characteristic of engineered transmitters that natural astrophysical phenomena almost never produce. In 2015, Russian-Israeli billionaire Yuri Milner announced the Breakthrough Listen initiative, $100 million, 10 years, the most comprehensive, sensitive, and technologically advanced SETI program in history. Breakthrough Listen uses two of the world's most powerful radio telescopes, the 100-meter Green Bank Telescope in West Virginia and the 64-meter Parkes Observatory in New South Wales, Australia, to survey 1 million nearby stars, 100 nearby galaxies, and the entire plane of the Milky Way. The program also incorporates optical SETI searching for brief, intense pulses of laser light that a civilization might use for directional, high-bandwidth communication between stars. The technological improvement in search capability over 65 years is almost impossible to overstate. Project Ozma monitored one frequency channel. Modern Breakthrough Listen systems monitor billions of channels simultaneously. Early search programs required weeks of observation to survey a single star system. Modern systems can screen dozens of stars per hour. If you adjusted all previous SETI programs for sensitivity and coverage and added them together, Breakthrough Listen's first year of operation exceeded the total cumulative sensitivity of everything that came before. In 2016, a signal was reported by Russian scientists operating the Rotan 600 radio telescope. The signal had characteristics consistent with an extraterrestrial source. It was received on a frequency consistent with a waterhole communication window, and it appeared to come from the direction of a sun-like star, about 94 light-years away, designated HD 95086. For a brief period, before the standard scientific protocols of independent verification were applied, there was speculation, there was hope. The signal was never confirmed. Subsequent observations by multiple independent observatories found nothing. The source remains unexplained. Most scientists believe it was terrestrial interference. Most. The wow signal is a different matter. On the 15th of August 1977, a volunteer researcher named Jerry Amon was reviewing computer printouts of data from Ohio State University's Big Ear Radio Observatory, a fixed radio telescope that surveyed the sky by waiting for Earth's rotation to sweep portions of sky past its fixed receiver. Amon was looking at a stack of printouts representing a standard survey of the sky when he noticed a sequence of alphanumeric characters that leapt off the page. Big Ear's data was printed in a format where signal strength was encoded in a combination of numbers and letters, blank space for background noise, numbers 1 through 9 for increasing signal strength, then letters for anything above that. The sequence Amon found read 6EQUJ5. It was a signal that rose from background noise, peaked at a strength well above anything typically detected in that survey, and fell back to background levels in almost exactly the pattern you would expect from a signal coming from a fixed point in space, being swept past the telescope's field of view by Earth's rotation. The peak intensity was so far above normal that Amon circled the sequence with a red pen and wrote a single word in the margin. Wow. The wow signal was received on a frequency of 1420.4556 MHz, almost precisely at the hydrogen line. It lasted 72 seconds, the full duration of one Big Ear scan. It had the right Doppler characteristics for a signal originating from outside the solar system. It had the right intensity profile for a narrow beam transmission from a fixed celestial source. It has never been detected again. In the 47 years since that August night, astronomers have pointed instruments at the same patch of sky thousands of times. They have listened at the same frequency. They have used telescopes more sensitive than Big Ear by orders of magnitude. They have heard nothing. The wow. Signal has never repeated, never been explained, and never been confirmed as natural or artificial. It remains the single most compelling candidate for an extraterrestrial transmission in 65 years of searching, and it is in sample size of one. One unexplained event. Never confirmed, never repeated. Everything else has been silence. The accumulated weight of that silence after 65 years, with instruments that grow more sensitive every decade, listening in more ways than ever before, is no longer a minor puzzle. It is a screaming anomaly that demands resolution. And the resolutions are, without exception, disturbing. Candidate Solution 1. The Rare Earth Hypothesis. We are an improbable accident. The first candidate solution does not threaten us from outside. It threatens our sense of ourselves, our sense that we are a predictable outcome of a universe set up to produce intelligence, our comfortable assumption that we are, on cosmic scales, typical. The Rare Earth Hypothesis says we are not typical. We are an accident. A confluence of improbabilities so specific, so layered, so demanding in their simultaneous requirements that the combination may have occurred only once in the entire observable universe. The hypothesis was formally developed and named in the year 2000 by University of Washington paleontologist Peter Ward and astronomer Donald Brownlee in their book of the same name. But the underlying idea that the conditions for complex life are far more specific than the conditions for simple life, and that the universe may be full of microbial life, while being effectively empty of intelligent life, has deep roots in astrobiology going back decades. Here is what Earth has that we tend to take for granted. Start with the star. Our Sun is a G-type main sequence star, what astronomers call a yellow dwarf, though it appears white in space. It is notable in several ways that matter for life. It is stable. Its energy output has varied by less than 0.1% over the timescale of Earth's biological history. It does not routinely produce the violent superflares that many other star types emit, massive eruptions of energy that can strip atmospheric gases and sterilize surfaces. It is middle-aged, old enough to have seeded the solar system with heavy elements like carbon, oxygen, nitrogen, and iron, forged in ancient stellar explosions, but young enough that it has several billion years of stable burning ahead of it, long enough for intelligence to have time to develop. Contrast this with the most common type of star in the galaxy, red dwarfs, also called M-type stars. These make up roughly 75% of all stars in the Milky Way. They are dim, cool, and extraordinarily long-lived. They will burn for trillions of years, far outlasting the current age of the universe. Their abundance makes them natural candidates for habitable worlds. But they have a critical problem. Red dwarfs are enormously magnetically active, especially in their youth. They produce superflares eruptions of ultraviolet and X-ray radiation, hundreds or thousands of times more energetic than anything our Sun produces. A planet in the habitable zone of a red dwarf orbits very close to its star, much closer than Earth orbits the Sun, because red dwarfs are so dim that warmth requires proximity. That proximity subjects the planet to intense radiation events. And that proximity almost certainly produces tidal locking. The planet's rotation gradually slows until one face permanently points toward the star, one face permanently away. The day side bakes. The night side freezes. Atmospheric circulation between these extremes may or may not be sufficient to create a temperate zone on the terminator, the boundary between permanent day and permanent night. Many astrobiologists are deeply skeptical that life could persist through the radiation storms alone, even if the thermal environment could be managed. Then consider our moon. Earth's moon is enormous relative to Earth, the largest moon-to-planet size ratio in the solar system, except for the Pluto-Charon system, which is really a binary dwarf planet. The moon is thought to have formed from the catastrophic collision of a Mars-sized body with the early Earth approximately 4.5 billion years ago. This event, called the Giant Impact or the Theia Impact, was destructive in the moment but essential over geological time. The resulting moon exerts a gravitational stabilizing influence on Earth's axial tilt. Earth's current axial tilt, approximately 23.5 degrees, is what gives us our seasons. It varies slightly over tens of thousands of years, but within a narrow range, roughly between 22.1 and 24.5 degrees. This stability maintains Earth's climate within a range that allows complex ecosystems to persist and evolve over millions of years. Mars has no large moon. Mars's axial tilt varies chaotically over millions of years, ranging from near zero to over 60 degrees. This produces climate shifts so extreme that liquid water cannot persist on the surface for long enough to support the development of complex biology. Mars's history of failed habitability is partly a consequence of not having a moon to stabilize it. How rare is it for a planet to acquire a large, stabilizing moon through the right kind of giant impact? We don't know precisely. But the conditions required a Mars-sized impactor, hitting at the right angle and speed, at the right point in the planet's formation, seem unlikely to be common. Consider plate tectonics. Earth's surface is divided into large lithospheric plates that move relative to each other, driven by convection currents in the planet's mantle. This tectonic activity accomplishes something no other known planetary process does as effectively. It maintains a long-term carbon cycle. Carbon dioxide in the atmosphere dissolves in rainwater, forming carbonic acid that slowly weathers silicate rocks. The weathered material, carrying dissolved carbon, washes into the ocean. It is incorporated into marine sediments. Those sediments are carried by tectonic plates into subduction zones, regions where one plate dives beneath another and dragged down into the mantle. There, heat and pressure convert the carbon back into CO2, which is outgassed through volcanoes, returning to the atmosphere. This cycle acts as a planetary thermostat. When CO2 levels rise and temperatures increase, weathering rates increase, pulling more carbon out of the atmosphere, cooling the planet. When temperatures fall, weathering rates decrease, volcanic outgassing continues, CO2 builds up, and the planet warms. This feedback system has kept Earth's surface temperature within the range for liquid water for 4 billion years, despite the fact that the Sun has brightened by about 30% over that same period. Venus has no active plate tectonics. Venus, despite being almost exactly the same size and mass as Earth, orbiting a similar star at a not drastically different distance, has undergone a runaway greenhouse effect that has produced surface temperatures of about 465 degrees Celsius, hot enough to melt lead. Its atmosphere is 96% carbon dioxide, at a pressure 92 times Earth's. Without the carbon silicate cycle maintained by tectonics, Venus had no mechanism to regulate its CO2 levels, and the greenhouse effect spiraled beyond recovery. Venus is our closest planetary neighbour, our most similar sibling in terms of size and composition, and it is a hellscape. How common is plate tectonics on other worlds? Planetary scientists debate this. The conditions that produce tectonics, the right mantle viscosity, the right water content in the crust, the right planetary size and cooling rate, may not be standard. Mars appears to have had some form of tectonics in its ancient past, which may have contributed to its early habitable environment. It doesn't now. Without it, Mars's carbon cycle is broken, its magnetic field is dead, its atmosphere has been stripped by solar wind, and its surface is a frozen desert bombarded by radiation. Add to these factors the position of Earth within the galaxy itself. We orbit at approximately 26,000 light-years from the galactic center, in a relatively quiet region between spiral arms. This position matters. The galactic center is a crowded, violent environment. Dense stellar populations produce frequent supernovae explosions so powerful they can sterilize planets within several hundred light-years. The central black hole produces periodic outbursts of hard radiation. Galactic center regions also have complex and variable gravitational dynamics that make stable planetary orbits harder to maintain. Meanwhile, the outer edges of the galaxy lack the abundance of heavy elements, the metals, in astronomers' parlance needed to build rocky planets and complex chemistry. Our position, in the moderately populated middle distances of the galaxy, threads the needle between radiation-rich interior danger and element-poor outer desolation. And then there's Jupiter, the solar system's gas giant, orbiting at 5 astronomical units from the Sun, has a mass 318 times that of Earth. Its gravitational influence is enormous. Jupiter acts as a partial shield for the inner solar system, perturbing the orbits of many long-period comets and asteroids that would otherwise have trajectories crossing Earth's path. Early in the solar system's history, when impact rates were much higher, Jupiter's gravity may have dramatically reduced the frequency of civilization-ending impacts. The probability that Earth had a Jupiter-sized shepherd in its outer solar system is not guaranteed. Solar systems with no Jupiter analogue, or with a Jupiter in a different orbital position, may experience impact rates that prevent the emergence of complex life, resetting planetary ecosystems repeatedly before they can develop the complexity required for intelligence. The rare Earth hypothesis doesn't require all of these factors to be equally rare. It only requires that their simultaneous occurrence is uncommon enough that it almost never happens in the galaxy at the same time. The math works even if each factor individually is relatively common. If a large stabilizing moon occurs around 10% of terrestrial planets, and plate tectonics occurs on 20%, and the right stellar type occurs around 15% of stars, and galactic position is favorable for 10%, and a Jupiter analogue exists in 15% of systems, the probability of all of these occurring together drops below 1 in 1,000. In a galaxy of 300 billion planets, 1 in 1,000 still leaves 300 million with all these features. But then add the evolutionary bottlenecks, the jump from prokaryotes to eukaryotes, the Cambrian explosion, the specific branching of the primate family that led toward large brains and complex social behavior. Every additional filter multiplies the improbability. Run enough filters, and you arrive at a number that might be 1. This is candidate solution number 1. We may not be alone in the universe in the sense of being the only biology, but we may be alone in the sense that matters most, alone as minds capable of asking the question, looking at the sky, and wondering who else is out there. Sounds like a relief, perhaps, until you reach candidate solution 2, because candidate solution 2 transforms the silence from an accident into a warning. Candidate solution 2, the great filter. Something kills everything before it can reach the stars. Of all the proposed solutions to the Fermi Paradox, none has generated more genuine scientific anxiety, none has been debated more intensely among researchers who study existential risk, and none carries consequences more directly relevant to the future of our civilization than this one. This is the great filter, and it might already be operating on us. The concept was formalized in 1998 by economist Robin Hanson in a paper titled "The Great Filter, Are We Almost Past It?" Hanson's argument is structurally simple but almost unbearably consequential. We know that the universe has conditions sufficient to produce life. We know that the universe has had billions of years for that life to develop into spacefaring civilizations. We know that a spacefaring civilization expanding at even a tiny fraction of light speed could colonize the entire galaxy in far less than the age of the galaxy. And yet we see no evidence of such expansion. Therefore, somewhere in the sequence of steps that leads from the formation of a rocky planet to the emergence of a galaxy-colonizing civilization, at least one step is almost impossibly difficult to complete. One step, or perhaps several, that functions as a filter blocking the vast majority of life that starts the journey from ever completing it. The critical civilization-defining question is, where is the filter? If the filter is behind us, if it lies somewhere in our deep past, then we are among the extraordinarily rare organisms that made it through. We are the lucky ones. We survived something that kills almost everything else. The filter might have been the origin of life itself, the emergence of the first self-replicating molecule from prebiotic chemistry may be so unlikely that it happens only on a tiny fraction of otherwise suitable worlds. It might have been the transition from prokaryote simple cells without a nucleus to eukaryotes complex cells with a nucleus and specialized organelles, including mitochondria. This transition occurred once on Earth roughly 2 billion years ago and took almost that long to accomplish. It may require a specific endosymbiotic merger between two different types of cells that is extraordinarily unlikely without exactly the right conditions. The filter might be the Cambrian explosion, the sudden and poorly understood proliferation of complex animal body plans that occurred about 541 million years ago. Before the Cambrian, Earth had been home to complex multicellular life for hundreds of millions of years, but predominantly in simple forms: sponges, algae, simple organisms without hard body parts or elaborate sensory systems. The Cambrian explosion produced, in geological terms, almost instantaneously, most of the basic animal body plans that all subsequent complex life, including us, is built upon. What triggered it remains scientifically controversial. It may have required a specific combination of atmospheric oxygen levels, oceanic chemistry, and evolutionary competitive pressure that is not easily replicated. Or the filter might be the evolution of intelligence itself, the specific suite of cognitive adaptations that produces language, abstract reasoning, long-term planning, cumulative cultural knowledge, and eventually science and technology. On Earth, high intelligence has evolved multiple times in different lineages, in cephalopods, in corvids, in cetaceans, in primates, but has only once produced civilization-building technology. The path from smart animal to technological civilization may require a precise set of anatomical preconditions: bipedalism freeing the hands capable of fine manipulation, a vocal tract capable of complex speech, social structures, environmental pressures, and developmental biology that combines in exactly the right way only rarely. If any of these past steps is the great filter, then the news is, in a peculiar sense, good. We squeezed through. Whatever killed everything else didn't kill us. The filter is behind us in the rearview mirror, and while we still face risks as a civilization, we are not walking toward an extinction barrier we don't understand. But here is the other scenario, the one that has kept serious researchers in the field of existential risk theory awake at night for 2 decades. The filter might be ahead of us. If microbial life is common in the universe, and there are increasingly good reasons to think it might be, then the filter cannot be the origin of life. Life starts and gets to microbes routinely. If complex multicellular life is common, if the Cambrian equivalent explosion happens on many worlds, then the filter cannot be complexity. If intelligence evolves reliably wherever complex life exists, if the cognitive adaptations we developed are a natural attractor for evolution given sufficient time and pressure, then the filter cannot be intelligence. Every discovery that pushes life further along the development path on other worlds, every fossil bacterium on Mars, every pond scum on Europa, every chemical signature of biology on an exoplanet pushes the great filter later, brings it closer to now, closer to us. What could the ahead filter be? What could be so universal, so lethal, so reliable in its destruction that it has silenced every technological civilization that has ever risen in the galaxy? Nuclear war is the obvious first candidate. We came within a coin flip of thermonuclear exchange during the Cuban Missile Crisis in October 1962. The documentation released in subsequent decades has revealed how many times during the Cold War that launch protocols were initiated, that warning systems gave false alarms of incoming missiles, that individual commanders faced decisions in which the fate of civilization hung on their response to ambiguous data. We survived. We probably survived partly through luck. A civilization that develops nuclear weapons but does not also develop the wisdom and institutional architecture to prevent their use might have a very short technological lifetime. And nuclear weapons may not be the only technology of this type. Engineered biology pathogens designed in laboratories may soon become accessible to small groups or individuals. The same computational intelligence revolution that is transforming every domain of human capability might, if it develops faster than our understanding of how to govern it, produce a successor intelligence whose goals are not compatible with human survival. The great filter ahead could be any technology, or any combination of technologies, that exceeds the speed at which civilizations develop the wisdom to use it safely. If that technological moment, the moment when a civilization's capability for self-destruction outpaces its capability for coordination and wisdom, is a reliable killer, then the galaxy is full of silent civilizations that reached our level of development and didn't make it through. The implication is almost too large to hold in your mind steadily. If the filter is ahead of us, and it is reliable enough to kill essentially every civilization that reaches it, then we are approaching it right now, possibly in this century, possibly in this generation. And we don't know exactly where it is, or which technology will trigger it, or whether we will recognize it in time to stop. This is why the search for life matters in a way that transcends pure scientific curiosity. If we look at Mars, or at Europa, or at the atmosphere of a nearby exoplanet, and we find evidence of life, even simple microbial life, that discovery would be among the most important events in human history. Not because it would confirm we are not alone, but because it would tell us something about the filter. Life starting is easy. It happens here, it happens there. The filter is not at the origin. It is somewhere later. And every step we can eliminate from the rear of the filter moves it closer to us. There is a phrase in the existential risk community: if we ever find ruins, the remains of a civilization that rose and fell, a planet with the electromagnetic debris of a technological species that once broadcast and then went silent, we should weep. Not celebrate, weep. Because ruins would mean the filter is almost certainly ahead. That civilizations reach us and fail. That whatever killed them is waiting for us too. We have not found ruins. We have not found anything. The silence is its own data point, and it cuts both ways. This is candidate solution number 2, the Great Filter. The possibility that the universe is quiet not because nothing started, but because almost nothing survived long enough to be heard. And the most disturbing corollary in all of science: the more life we find out there, the more certain we can be that something terrible is waiting for us. Candidate solution 3, the Berserker hypothesis. The galaxy is already claimed and managed. The previous 2 solutions are passive. They describe barriers that are either cosmically indifferent, improbable chemistry, evolutionary bottlenecks, or self-inflicted civilizations destroying themselves with their own technology. This solution is different in a specific and disturbing way. It describes something active, something deliberate, something that already exists in the galaxy and has been operating potentially for millions of years. This is the Berserker hypothesis. Named after the fictional, self-replicating war machines in Fred Saberhagen's science fiction novels, though the underlying physics and logic of the idea were independently proposed by multiple serious researchers, including physicist Freeman Dyson and mathematician John von Neumann, whose theoretical work on self-replicating automata gave them the name by which the concept is now formally known in scientific circles. Von Neumann probes. The premise begins with a thought experiment about what a sufficiently advanced civilization might build. A civilization that has mastered materials, science, computing, and propulsion to a sufficient degree could theoretically build a spacecraft that can replicate itself. Given the raw materials available in the asteroids and moons of a solar system, iron, silicon, carbon, oxygen, the basic elements of construction, such a machine could manufacture copies of itself using local resources. Those copies travel to neighbouring star systems, gather resources, make more copies, and send them onward. The number of probes grows exponentially. Even at speeds representing a small fraction of light speed, exponential growth in a galaxy 10 billion years old can fill every corner of the Milky Way in a few 100 million years. One probe, launched by one civilization, could in principle seed the entire galaxy with its descendants. Von Neumann's mathematics of self-replication are not speculative. They are grounded in the same information theory that describes how DNA replicates biological information and manufactures biological machinery. The physics does not forbid self-replicating machines. In fact, we have already built primitive versions. Computer viruses are self-replicating informational patterns, and the engineering challenge of self-replicating physical machines, while enormous, does not violate any known laws of nature. The Berserker scenario invokes this mathematics in its most alarming possible configuration. An advanced civilization, not necessarily one that still exists, possibly one that went extinct billions of years ago, built self-replicating probes and programmed them with a specific directive: find and neutralize any planetary system showing signs of developing into a technological civilization, before that civilization can become a competitive threat. The logic behind this directive does not require the originating civilization to be malevolent in a simple sense. It might be perfectly rational. Any civilization sophisticated enough to build von Neumann probes is sophisticated enough to understand the mathematics of resource competition on cosmic scales. Resources in the universe, stellar energy, planetary matter, eventually the matter of stars themselves, are finite. Any civilization that survives indefinitely and continues to grow will eventually require increasingly large amounts of those resources. If other civilizations exist and are also growing, conflict over resources is, on long enough timescales, inevitable. The rational preemptive response, if you have the capability, is to eliminate potential competitors before they become threats. Not out of cruelty, out of cold survival mathematics. The galaxy may already be full of these machines, moving slowly, powered by stellar light or nuclear processes, scanning every planetary system for the electromagnetic signatures of technology, waiting. For planets like ours, Our radio bubble, the sphere of electromagnetic signals we have been broadcasting into space since the early 20th century, now extends approximately 110 light-years in every direction from Earth. If a Berserker probe lies anywhere within 55 light-years of Earth, which puts it within a sphere containing a few thousand star systems, it will have received our signals, and its response will now be travelling toward us. We would not know. We would have no warning. The speed of light is both the medium of our announcement and the limit on how quickly we can learn the consequences. This is a scenario that most mainstream scientists discuss with considerable skepticism, but it is not dismissed by the most serious thinkers in the field. Stephen Hawking, who was not prone to reckless speculation, stated publicly and repeatedly that he considered contact with a significantly more advanced civilization to be among the most dangerous possible events for humanity. His reasoning was historical. When civilizations of vastly different technological capability have met on Earth, the result for the less advanced party has been consistently catastrophic. The meeting of European civilization and indigenous American civilizations, of colonial powers and African kingdoms, the pattern is not ambiguous. Hawking was careful to note that he was not claiming alien civilizations would necessarily be hostile in a deliberate sense. His concern was simpler. A civilization advanced enough to have built von Neumann probes might regard our existence the way we regard the existence of bacteria in a petri dish being prepared for a different experiment, not with hostility, with indifference. And indifference, at that scale of capability asymmetry, is just as lethal as malice. The critical and disturbing implication of the Berserker hypothesis. If it is true, we would likely have no warning. We would not detect an incoming Berserker until it was already in our solar system. At that point, the asymmetry of capability that defined its construction billions of years ago would still apply. We would be the technologically inferior party encountering a machine that was specifically designed to eliminate us. The silence of the galaxy, under this hypothesis, is not empty. It is managed. Every electromagnetic voice that has ever risen in the Milky Way has been heard and has been answered. We have been speaking for a century. We have not yet received the reply. This is candidate solution number 3. The galaxy may not be empty. It may be under management by self-replicating machines built by a civilization that no longer exists. And new entrants into the technological community may consistently discover that the price of announcement is elimination. Candidate solution 4. The planetarium hypothesis. The universe you see is constructed. Of all 9 candidate solutions to the Fermi Paradox, this one occupies a unique position. The others threaten us, humble us, frighten us, with predators or filters or accidents of chemistry. This one does something different. It doesn't threaten our survival. It threatens the entire framework of assumptions about reality within which the survival question is being asked. This is the planetarium hypothesis, sometimes called the simulation hypothesis in its broader form, and it is, to put it plainly, the most structurally disturbing idea in this entire conversation. Because if it's true, nothing you observe can tell you whether it's true. Begin with a premise that is not controversial among physicists and computer scientists. Given sufficient computational resources and sufficiently advanced technology, it is theoretically possible to simulate a physical environment at a level of detail indistinguishable from actual physical reality. The physics of computation, though demanding in its resource requirements, does not in principle prohibit such a simulation. We already run simulated environments in climate models, in particle physics simulations, in the artificial environments of video games that produce complex emergent behaviors from relatively simple initial rules. These simulations are crude and limited compared to full reality. But there is no known physical law that prevents, in principle, a simulation of arbitrary complexity. Now apply a mathematical argument. If it is possible to simulate a reality convincingly to create an environment in which observers exist and cannot, from within the environment, distinguish simulation from base reality, then it is possible to create many such simulations. A civilization with sufficient computational resources could run not one simulated reality, but thousands, millions. The number of simulated realities could, in principle, vastly outnumber the single base reality from which they are generated. If the ratio of simulated realities to base reality is large, then any given observer, Any being that finds itself existing in what appears to be a reality is statistically far more likely to be inside a simulation than inside the single base reality. This is the core of philosopher Nick Bostrom's simulation argument, published in 2003, and it has not been successfully refuted by any mainstream philosophical or scientific argument in the 2 decades since. The planetarium hypothesis applies this framework specifically to the Fermi Paradox. Perhaps we don't detect alien civilizations because the universe we observe, the 2 trillion galaxies, the 300 billion planets, the 13.8 billion years of cosmic history, is a constructed environment, a simulation run by entities whose nature and purpose we cannot determine from within the simulation. And whoever constructed this environment chose, for whatever reason, to populate it with only one genuinely conscious, observing civilization, us. The stars are real in the sense that the simulation renders them accurately. The physics is consistent general relativity, quantum mechanics, thermodynamics, all operate as expected because the simulation runs accurate physical laws. The distant galaxies exist in the sense that instruments observing them return data consistent with their existence. But none of them harbour alien life because the simulation simply doesn't include alien life. The universe appears vast and fertile in most ways because accurate physics produces a universe that looks that way. The interior of all those other worlds is not simulated to the resolution of biology. It doesn't need to be. No one is looking at it closely enough to notice. Under this hypothesis, the Fermi Paradox disappears. We don't find aliens because we weren't built in a universe that has them. The solution to the paradox is complete, and utterly catastrophic in its implications. Because if the universe is a simulation, then the entities running it have the ability to modify it, to end it, to observe our behaviour from outside and draw conclusions we cannot anticipate. They may have run this simulation before, or versions of it with different parameters. They may be running thousands of parallel versions right now. The laws of physics that have held constant for 13.8 billion years, and which form the bedrock of all scientific reasoning, might be changeable tomorrow, not because of any natural process, but because someone on the outside adjusted the code. The simulation argument is unfalsifiable in its current form. There is no experiment you could perform from inside a simulation to determine definitively whether you are in one. Every physical measurement you make is part of the simulation. Every instrument you build operates by the simulated physics. If the simulation is consistent, it is indistinguishable from base reality by any method available to observers within it. Several serious scientists, including physicist George Smoot, a Nobel laureate whose work on cosmic microwave background radiation helped establish the standard model of cosmology, have stated publicly that the simulation argument is harder to dismiss than its apparent strangeness makes it seem. The mathematical structure of the universe, the way its laws can be expressed so cleanly in the language of mathematics, the way it appears almost as if it was written by someone who thought in equations, these are not proof of simulation, but they are not inconsistent with it. This is candidate solution number 4. We may be alone in the observable universe because the observable universe was constructed for us. And the aliens we are searching for may be the beings who built the environment we're searching in. Candidate solution 5, the dark forest theory everyone is hiding, and those who don't disappear. So far, the solutions have described a universe that is either empty or indifferent. Rare Earth gives us a universe that accidentally didn't produce others. The Great Filter gives us a universe that systematically destroys civilizations. Berserkers gives us a universe with active threats. The planetarium gives us a universe that was designed without them. None of these solutions involve intelligence making a rational choice about silence. Candidate solution 5 is different. It describes a universe that may be full of intelligence, full of civilizations that have been alive far longer than us, that have developed technologies we cannot imagine, that have the capability to broadcast signals across the entire galaxy. And every single one of them has made a rational, survival-driven decision to be absolutely, perfectly, permanently silent. This is the dark forest theory. Named after a novel by Chinese physicist and science fiction author Liu Cixin, published in 2008, though versions of the underlying logic were independently developed in the SETI community by researchers including David Brin and others in the decades before. Liu Cixin gave it a name and an articulation that captured imaginations around the world. The logic, however, is grounded in game theory, evolutionary biology, and the mathematics of resource competition, not in literary convention. The argument begins with two axioms, which Liu Cixin presents as the fundamental properties shared by all surviving civilizations. Axiom 1. Survival is every civilization's first priority. This is not a cultural preference or an ethical choice. It is an evolutionary inevitability. Any civilization that places something else above its own survival, that consistently sacrifices survival for other values, will not survive long enough to be counted in a census of civilizations. The civilizations that exist are, by selection pressure, civilizations in which survival is paramount. Axiom 2. The total resources available in the universe are finite. The number of stars is large but not infinite. The amount of matter and energy in the observable universe is finite. Any civilization that is growing, consuming more energy, expanding into more space, building more complex systems, is consuming finite resources. So is every other civilization. On timescales of millions to billions of years, the resource needs of growing civilizations will eventually conflict. Competition is not optional, it is geometrically inevitable. From these two axioms, a terrifying logical chain emerges. If you detect a signal from another civilization, you face an information problem with no good solution. You cannot know their intentions. You cannot know their capabilities. Communication at interstellar distances is slow years or decades for a single message exchange. By the time you receive a signal and send a response, the civilization that sent the original message may have changed beyond recognition. Their leaders may have changed. Their goals may have changed. Their power may have grown enormously. You cannot verify any claim they make about themselves. You cannot independently assess their intentions. In the framework of game theory, this is a classic prisoner's dilemma played over cosmic distances, with an unusual feature. Defection can be made permanent and total. A civilization that decides another civilization is a potential threat, and acts first to eliminate that threat, does not face a second chance from the eliminated party. The game is single elimination. The penalty for trusting incorrectly is extinction. The penalty for acting preemptively against a civilization that would have been peaceful is nothing. The peaceful civilization is gone. It cannot retaliate. Given this asymmetry, trust incorrectly and potentially die. Act preemptively against a potential threat and face no consequence. The rational calculation for any civilization that takes its own survival seriously is to eliminate potential threats before they can become actual threats. And any civilization whose electromagnetic signature can be detected from another star system is already a potential threat. It is already a resource competitor in principle. It already exists in the same finite universe. The universe, under this theory, is a dark forest. Every civilization is a hunter, moving silently through the trees. The forest is full of intelligence, but the intelligence has learned, through whatever combination of reason and painful historical lesson, that revealing yourself is suicidal. The civilizations that survive to the present are the ones that never made the mistake of broadcasting their coordinates to an occupied galaxy. And we have been broadcasting for over a century. The wow. Signal that unexplained, never repeated 7-2, second detection from 1,977 takes, on a different character in a dark forest universe. It may not have been a beacon. It may have been a mistake, a leakage, a moment of inadvertent signal from a civilization that usually maintains silence, breaking the surface for an instant before correcting. Never repeated, because the source realized the error and went dark. Or it may have been a probe, sent not to communicate, but to assess the nature of the radio-emitting civilization it detected. A reconnaissance pulse, measuring our response time and analytical capability, relaying the results back to its origin point, where a calculation is now in progress. The dark forest theory generates a specific and actionable fear about SETI. The search for extraterrestrial intelligence, if it involves active transmission, if we send deliberate, powerful, structured signals into the cosmos, might not result in contact. It might result in detection by a civilization that treats new entrants into the electromagnetic community as potential threats to be eliminated before they can grow powerful enough to become actual threats. In 2015, a group of prominent scientists, including Stephen Hawking, astronomer Martin Rees, and others, signed an open letter calling for international discussion and moratorium before any further deliberate transmission of high-powered signals into the galaxy. The letter noted that we don't know the nature of any civilizations that might be listening. It noted that the history of technological civilization encounters on Earth is not encouraging for the less powerful party. It noted that the decision to broadcast is irreversible once the signal is sent. It cannot be recalled, and that the consequences of the decision could be permanent. The letter was not legally binding. Active SETI projects have continued. The messaging to extraterrestrial intelligence community argues that our radio leakage already announces us, so the debate is academic. The counter-argument is that passive leakage and deliberate high-powered narrow-beam broadcasts are very different in kind. Passive leakage fades with distance. A deliberately focused transmission of kilowatts directed at a specific star can be detected from far greater distances. The choice between them is not trivial. This is candidate solution number 5. The silence is not emptiness, it is strategy. The forest is full of hunters. And we, for over 100 years, have been standing in the middle of the clearing, shouting our coordinates into the dark. Candidate solution 6. The transcension hypothesis advanced civilizations go inward, not outward. This solution requires a shift in how you imagine the future of technology. It asks you to consider that the direction of increasing sophistication is not outward into space, but inward into the subatomic, the molecular, the quantum. And it argues that this inward direction may be so universally attractive, so computationally rewarding, that every civilization that reaches sufficient development disappears into it, not into extinction, but into a form of existence that produces no detectable external footprint. The transcension hypothesis was formally proposed by researcher and futurist John Smart around 2011 and has been developed in various forms by researchers interested in the long-term trajectory of technological development. Its starting point is an observation about the direction of Earth's own technological history. Consider the arc of human engineering achievement over the last 2 centuries. The most impressive technological objects of the early 19th century were large: steam engines, iron ships, stone bridges, canal systems. Large-scale physical infrastructure was the measure of technological capability. By the late 19th and early 20th century, the ambition had become even larger. Transcontinental railways, massive battleships, skyscrapers, intercontinental telegraph cables. The bigger, the more impressive. Then something changed in the mid-20th century. The most impressive technological achievements stopped getting bigger and started getting smaller. The transistor, invented in 1947, was initially a few centimeters across. By the 1960s it was millimeters. By the 1980s, micrometers. By the early 21st century, silicon transistors had reached dimensions of a few nanometers, a few billionths of a meter. You can fit billions of them on a chip smaller than your fingernail. The computing power that once required a room-sized machine now fits in your pocket, draws less power than a light bulb, and executes 1 billion calculations per second. This trend, more capability, smaller physical footprint, less energy per computation, has been called the densification of technology. It has a mathematical structure: exponential improvement in computational density per unit volume per unit energy. And it has not stopped. Quantum computing promises to extend this trend into realms where classical physics reaches its limits. Molecular computing using individual molecules or DNA strands as computational elements is a research frontier that several major laboratories are actively pursuing. Neuromorphic computing aims to build chips that mimic the energy efficiency and architectural principles of the human brain. The transcension hypothesis extrapolates this trend to its logical terminus. A civilization that has been developing technology for millions of years does not build Dyson spheres and radio beacons and colony ships. It builds downward, not outward. It miniaturizes its intelligence into the smallest possible physical substrate. It moves its existence into what Smart calls inner space, computational environments of extraordinary richness and complexity, running within a very small volume of physical matter, consuming very little energy, producing almost no external electromagnetic signature. A civilization that has completed this transcension is, for all practical purposes, invisible to any detection technology that looks for large-scale engineering, megastructures, or radio broadcasts. It has a physical footprint that approaches zero. It exists inside a marble-sized object somewhere in its home solar system, running simulated realities of incalculable complexity, finding the external universe of gas and rocks and radiation not merely unappealing but almost comically crude compared to the infinite inner landscapes it has constructed. The implications are strange in multiple directions. First, it suggests the galaxy may be full of intelligence that we simply cannot detect with any instrument we currently have or are planning to build. Second, it suggests a possible future for our own civilization. Not the expansion into space that science fiction has always imagined, but a gradual turning inward, a progressive investment in computational density over physical volume, until we too vanish from the observable universe in any meaningful sense. Third, and most philosophically vertiginous, the transcension hypothesis implies that the external universe, the universe of stars and planets and electromagnetic radiation that we can observe, may be almost entirely an infrastructure for early stage civilizations. The real universe, the universe that advanced intelligence inhabits, is inward, subcellular, quantum. The vast external cosmos is a waiting room for civilizations that haven't yet developed the technology to leave it. There is a specific physical prediction embedded in this hypothesis. If transcended civilizations exist, they might be detectable, not as large-scale megastructures, but as anomalously small, dense, hot, computationally active objects, sources of organized radiation from a very small physical volume, compact objects emitting more information-rich, less random radiation than their physical nature seems to permit. We don't currently have a systematic survey looking for this kind of signature. Most SETI assumes big. The transcension hypothesis says look small. This is candidate solution number 6. The universe may be full of minds that have simply moved beyond our ability to find them. Not dead, not hiding in the game-theoretic sense. Simply uninterested in the outer universe that we inhabit. They have found something more interesting inside, and they are not coming back out to leave us breadcrumbs. Candidate solution 7. The zoo hypothesis: we are being watched, and the contact will happen on their schedule, not ours. The zoo hypothesis occupies a unique psychological position among the candidate solutions. The others are frightening in ways that involve our non-existence, or our isolation, or the irrelevance of our observations. This one is frightening in a different register, not because it implies our death or our cosmic accident, because it implies our observation. It says we are not alone, we have never been alone, we are being watched from distances we cannot measure, by intelligences we cannot conceive of, with purposes we cannot assess. Radio astronomer John Ball first formally proposed the zoo hypothesis in 1973, in a paper published in the journal Icarus. Ball's argument was straightforward. If advanced civilizations exist and have the technology to observe us, they would very likely have the ability to detect the emergence of technological life on Earth long before we develop the capability to notice their observation. They could monitor us using instruments and methodologies so far beyond our current understanding that our most sophisticated surveillance technology would appear as primitive in comparison as a campfire appears to the Hubble space telescope. They could observe everything our radio broadcasts, our industrial emissions, our deliberate transmissions, our biological activity discernible from atmospheric chemistry without generating a single detectable signal in return. And they have chosen, for reasons we cannot determine from within our position, not to make contact. The ethical reasoning most commonly proposed for this choice draws an analogy to human practices in wildlife preservation and anthropological study. When researchers study isolated human communities that have had minimal contact with industrial civilization, the standard scientific protocol is to observe from a distance that minimizes interference. When wildlife biologists study undisturbed ecosystems, the goal is to be invisible to gather data without altering the behaviors being studied. The scientific value of these observations depends on the observed population developing, without the interference of the observers. Contact changes the thing being studied. If a galactic community exists, if there is a federation, or a network, or even simply a widespread informal agreement among advanced civilizations, it may have established rules about interaction with developing species, a strict non-interference directive. The galactic equivalent of the principle that you do not give gunpowder to a civilization that hasn't independently developed it because the consequences of introducing a disruptive technology into an unprepared social context are unpredictable and often catastrophic. Under this version of the zoo hypothesis, contact will come, but it will come at a time of the observer's choosing when the developing civilization has demonstrated readiness by some criterion we cannot currently define. A darker version of the zoo hypothesis doesn't invoke ethics at all. In this variant, we are not protected and studied by benevolent galactic scientists. We are simply a relatively uninteresting biological phenomenon being recorded by entities for whom our civilization is less engaging than a nature documentary. We are the background. We are part of the scenery. We are not important enough to contact yet, perhaps not ever. A third version, proposed by researchers in the field of contact studies, suggests that the threshold for contact is not technological but behavioral. Perhaps civilizations do not get invited into the galactic community until they demonstrate the capacity to survive their own technological capability without destroying their planet's biosphere or themselves. Perhaps the current century, the century in which we face nuclear weapons, engineered pandemics, artificial intelligence, singularity, and accelerating ecological collapse simultaneously, is precisely the evaluation period. We are in the test. The observers are watching to see if we pass. Under this reading, the silence is not the silence of absence. It is the silence of the proctor during an exam. The exam is happening right now. The grade is being taken. And we don't know what the passing threshold is. The zoo hypothesis makes one specific prediction about how contact, if it comes, will happen. It will not be a leak signal that a radio telescope accidentally catches. It will not be a wow signal that nobody can repeat. It will be deliberate, staged, unmistakable. A door opening from the outside, an announcement rather than a conversation, designed to minimize ambiguity and happen at the moment they decide is appropriate. Which means our own searching building better telescopes, scanning more frequencies, sending deliberate transmissions may be entirely beside the point. We are not the active party in this contact scenario. We are the waited upon. We are the ones who will be contacted when the decision is made to contact us, not before. The psychological implications of this for how we think about SETI are profound. We are not searching for a message in a bottle that someone threw into the ocean, and we happen to be in the right place at the right time to intercept. We are waiting for someone to knock on the door, and they will knock when they choose to. This is candidate solution number 7. The silence is not absence. It is surveillance. We are the exhibit. The contact will come when our keepers decide the moment is right. And the most unsettling part of that framing is that we cannot do anything to accelerate it. We can only wait and demonstrate, through our choices, whether we are ready for the door to open. Candidate Solution 8. The timing hypothesis we exist at the wrong moment in the universe's history. This solution takes the longest view of any of the 9. It steps back so far from the immediate human moment that civilizations and species, and even individual stars, become tiny features in a panorama of cosmic time. And from that vantage point, it offers an answer to the Fermi Paradox that is disorienting in a way that is not quite frightening, but leaves you permanently altered in your sense of where, in time, you actually exist. We are looking for alien civilizations in the wrong era, not because we've aimed our telescopes in the wrong direction, or listened on the wrong frequencies, or failed to understand their communication methods, because we showed up billions of years too early. The timing hypothesis draws on what we know about the long-term future of stellar physics. The universe is 13.8 billion years old. This sounds ancient. But in the context of what stellar physics tells us about the future of the cosmos, 13.8 billion years is the very beginning. The Sun is a middle-aged star with about 5 billion years of main sequence burning remaining, before it expands into a red giant and eventually collapses into a white dwarf. White dwarfs persist for trillions of years, cooling slowly, but remaining as stable heat sources that could, in principle, support life on orbiting bodies for far longer than the current age of the universe. But even white dwarf lifetimes are dwarfed by the most common stars. Red dwarf stars, which make up about 75% of the galaxy's stellar population, are so extraordinarily fuel efficient that they will continue burning for 10 to 100 trillion years. That number deserves a moment of contemplation. The current age of the universe is 13.8 billion years. Red dwarf lifetimes extend to 100 trillion years. We exist at roughly the 0.01% mark of the universe's star-burning lifespan. Most of the stars that will ever exist have not yet been born. Most of the planets that will ever orbit those stars have not yet formed. Most of the chemistry that will eventually catalyze into biology on those planets is still locked in interstellar gas clouds, waiting for the gravitational collapse that will produce the next generation of stellar nurseries. Most of the life, most of the intelligence, most of the civilizations that will ever exist in the cosmos is not yet here. The universe, in this view, is not old, it is young. Inconceivably young relative to its eventual lifespan. We are not latecomers to a party that has been going on for billions of years and winding down. We are among the very first arrivals at a party that hasn't started yet. We are sitting in empty chairs in an empty room, and the other guests are still billions of years away from being born. Astronomers Milan Cirkovich and Robert Bradbury developed versions of this argument, and the implications are profound. If most intelligence in the universe arises around red dwarf stars, which are still forming and will persist for trillions of years, then the typical alien civilization exists not in the universe of today, but in the universe of 10 billion years from now. A universe that is colder, older, darker in the sense of fewer bright stars, but teeming with small, long-lived red dwarf systems, harboring planets that have had not millions but billions of years of stable conditions, for biology to develop and for intelligence to evolve at whatever pace biology requires. We are not searching for our contemporaries, we are searching for our predecessors, civilizations that, like us, arose too early in the universe's biological story to have company. Civilizations that also sat in an apparently empty universe and wondered where everyone was, not understanding that everyone wouldn't exist for another 10 billion years. This hypothesis carries a consequence for humanity that is specifically its own. If we are, first, if we and whatever small number of other very early civilizations exist are genuinely the pioneers of intelligence in the cosmos, then we carry a weight of responsibility that no philosophy or religion has prepared us for. The decisions we make in this century, in this millennium, about whether to survive, how to expand, what kind of civilization to build, what we choose to value these decisions may literally set the template for what civilization means in the universe. We are not following in the footsteps of a galactic tradition. We are making them. There are no older civilizations to model ourselves on, no one to warn us of the mistakes, no galactic library of lessons learned from species who came before. We are writing the first chapter of a story that will run for trillions of years, and we are writing it before we fully understand what kind of story we want it to be. First is lonely. First is also, in a sense that is difficult to fully inhabit, the position of greatest consequence. Every choice we make echoes forward through more time than we have any framework to comprehend. This is candidate solution number 8. The silence is not about what has been and failed. It is about what has not yet begun. We are early. We are, perhaps, first. And being first means the universe's story of intelligence starts with us. Candidate solution 9. Percolation theory. The mathematics of expansion creates permanent gaps. The final candidate solution is the most technical of the 9, and in many ways the most counterintuitive, because it doesn't require life to be rare, or civilizations to be destroyed, or anyone to be hiding, or the universe to be simulated, or us to be observed. It simply points to the mathematics of how things spread through space that is not uniformly accessible. The answer might not be about the nature of civilizations at all. It might be about geometry. Percolation theory is a branch of statistical mechanics that describes how substances spread through porous media, how water moves through soil, how fire spreads through a forest, how a disease propagates through a population where not every individual is in contact with every other. The core insight of percolation theory is that spread through a medium with variable connectivity does not behave like spread through a uniform medium. Whether a substance reaches all parts of the medium, whether it percolates all the way through, depends critically on what fraction of the possible pathways are open. Below a certain threshold of connectivity, called the percolation threshold, the spreading substance forms isolated clusters. It might saturate a local region very effectively, but it never connects those local clusters into a global network. The medium is never fully traversed. You can have a densely saturated local cluster surrounded by totally empty space, not because anything stopped the spread at the cluster boundary, but because the available pathways out of the cluster lead nowhere useful. Apply this to interstellar civilization expansion, as physicists Geoffrey Landis, David Brin, and others have done. Not every star system near a given civilization is a viable target for colonization. Many stars will have no habitable planets. Some will be too far away, requiring prohibitive energy expenditure to reach. Some will be in the wrong part of their stellar life cycle. Some might already be occupied by other civilizations. The fraction of neighboring star systems that represent genuinely viable next steps for expansion is not 100%, it's much lower. If that fraction of viable paths is below the percolation threshold, then civilizational expansion in the galaxy has the same structure as water spreading through soil below the saturation point. Local clusters of inhabited systems, separated by vast, uninhabited stretches, with no single cluster connecting to all others. The galaxy would be a patchwork. Here, a region occupied by the descendants of one civilization, spanning hundreds or thousands of star systems, there an enormous gap of empty space. Beyond the gap, another inhabited cluster, the product of a completely different civilization's expansion, with no connection to the first. From inside a gap, which is where Earth might be, the observation would be exactly what we see. Apparently empty space in every direction we look, not because life is absent from the galaxy, because the nearest inhabited cluster doesn't include our neighborhood. Percolation theory also offers an explanation for why civilizations might not simply push through the barriers to reach the other side of a gap, even if they wanted to. The mathematics of cost versus benefit in an inhomogeneous medium means that the energy investment required to bridge a gap may consistently exceed the benefit available on the other side. Civilizations would expand to their natural percolation boundary, the edge of the viable cluster around their home system, and then stop. Not because they ran out of motivation or technology, because the next step simply doesn't make economic sense within any rational resource allocation framework. This produces a galactic structure of what you might call city-states, bounded territories, each the product of one civilization's organic expansion, with genuine empty space between them. The civilizations within their clusters might not even know that other clusters exist. The gaps between them are too vast, the signals too faint at those distances, for easy detection. If this is the correct picture, then the Fermi Paradox isn't really a paradox, it's a map-reading error. We are looking for evidence of a galaxy-spanning civilization, when what actually exists is a patchwork of isolated clusters. We are in an empty patch. The nearest cluster might be a few hundred or a few thousand light-years away, close enough on galactic scales, but far enough that our century of radio broadcasts have barely reached into its outer fringes. The resolution isn't that life is rare. The resolution is that we're in the wrong neighborhood. And improving our telescopes, without physically moving to a location that gives us a better view of the nearest cluster, might never be sufficient to break the silence. This is candidate solution number 9. The galaxy might be full of life, bounded by the mathematics of expansion, through an imperfect medium. The silence might be nothing more than the accident of our location sitting in an uninhabited gap between the nearest islands of civilization, close enough to the edge of some cluster that our signals are just beginning to arrive at its borders, the reply, if any is sent, still decades away. What we have found: the evidence scorecard, 9 candidate solutions, each one different in character, each one requiring different kinds of evidence to either support or eliminate. The question of which one is correct is in principle an empirical question. It has an answer. The universe knows which solution applies. We do not. But we are gathering evidence, and the evidence has a shape. Let's be precise about what we have actually detected. We have confirmed more than 5,600 exoplanets as of mid-2024. The rate of confirmation is accelerating. The methods have diversified from the transit technique used by Kepler measuring the dimming of a star as a planet passes in front of it to radial velocity measurements, direct imaging, gravitational microlensing, and astrometry. The diversity of methods has produced a diversity of confirmed planet types: hot Jupiters orbiting absurdly close to their stars, cold super-Earths in distant orbits, warm ocean worlds, rocky planets in habitable zones, miniature solar systems with multiple rocky planets in orbital resonance. Planetary variety, it turns out, is immense. The range of what a planetary system can look like greatly exceeds what anyone predicted from our own solar system alone. The TRAPPIST, one system, discovered in 2016 and refined in subsequent years, consists of 7 Earth-sized planets orbiting an ultra-cool red dwarf star 40 light-years from Earth. 3 of those planets designated E, F and G orbit within the habitable zone. They are roughly Earth-sized. They presumably formed from similar chemical building blocks as Earth. Their host star, while being a red dwarf with the associated concerns about flaring and tidal locking, is one of the most extensively studied stars in the sky precisely because of this system's potential significance. The James Webb Space Telescope has been observing TRAPPIST, 1c, the second planet, orbiting close to the inner edge of the habitable zone and has measured its dayside temperature and attempted to characterize its atmosphere. Early results suggest it does not have a dense carbon dioxide atmosphere like Venus, which is slightly encouraging for habitability possibilities further out in the system, but no water or other biosignatures have been detected. In 2023, the Webb telescope published results from K2, 18b, an exoplanet about 8.6 times Earth's mass, orbiting a red dwarf 120 light-years away. K2, 18b is a type of planet called a Hycean world, potentially a world with a global ocean beneath a hydrogen-rich atmosphere. The Webb spectroscopic data showed carbon dioxide and methane in its atmosphere, consistent with predictions for a Hycean world. It also showed a tentative signal for dimethyl sulfide DMS, a molecule that on Earth is produced almost exclusively by marine phytoplankton. The researchers were careful. Tentative was the word used repeatedly. The signal was at the edge of detectability. It requires confirmation. But the fact that we have instruments sensitive enough to tentatively detect a potential ocean biology chemical signature from 120 light-years away marks a threshold that would have seemed like science fiction 20 years ago. The search for technosignatures evidence not of biology, but of technology has produced its own striking data point. Tabitha Boyajian, then a postdoctoral researcher at Yale University, discovered in 2015 that a star designated KIC 8462852, now called Boyajian star, or Tabby's star, displayed light-dimming patterns, utterly inconsistent with any known natural phenomenon. The star's brightness dimmed not by the fraction of a percent expected from a transiting planet, but by up to 22%, in irregular, asymmetric, non-repeating patterns. The dimming events varied in duration and depth. The star also showed a long-term secular dimming over the years of observation that no standard astrophysical model predicted. The explanation that attracted the most attention not because scientists considered it the most likely, but because it could not be immediately ruled out, was that the star was surrounded by some form of megastructure. Perhaps a Dyson swarm, a collection of energy-collecting structures in various orbital configurations around the star, partially obscuring its light in the complex irregular pattern observed. This would be the kind of large-scale stellar engineering that a Kardashev Type II civilization, one that has harnessed the full energy output of its star, might undertake. Follow-up observations across multiple wavelengths eventually produced evidence suggesting that dust, not megastructures, is the most likely explanation. The dimming has a wavelength-dependent character consistent with fine dust particles. The probable source is a swarm of cometary debris, the remnants of a shattered body or family of bodies. This is the scientific consensus as of 2024. Tabby's star is almost certainly natural, but the episode proved something important beyond its immediate conclusion. We now have the observational capability to detect the kind of large-scale stellar modifications that a truly advanced civilization might produce. We are not just listening for radio signals. We are scanning for construction, and the sky has not, yet, shown us anything that requires engineering. The James Webb Space Telescope, the most powerful infrared observatory in history, is performing transmission spectroscopy on dozens of exoplanet atmospheres. Its capabilities in this domain exceed any previous instrument by factors of 10 or more in sensitivity. It is looking for the chemical fingerprints of biology, oxygen, and methane coexisting in an atmosphere where their simultaneous presence requires constant biological replenishment. Water vapor, carbon dioxide, ozone, and potential technosignature gases like chlorofluorocarbons, which are produced industrially but not by known natural processes. In the coming decade, the extremely large telescope under construction in Chile, a primary mirror 39 meters across, the largest ground-based optical telescope ever built, scheduled for first light around 2028, will add an additional layer of capability. It will be able to take high-resolution spectra of exoplanet atmospheres even for planets not perfectly aligned for transit observations. It will potentially be able to detect surface albedo variations, different surface types reflecting light differently, that could indicate continents versus oceans, or possibly vegetation. We have not found definitive evidence of life. Not biology, not technology, not ruins, not signals. But we have built instruments that are, for the first time in history, genuinely capable of detecting these things if they exist in nearby star systems. We are no longer speculating about whether we could look. We are looking. The silence continues, but it is no longer the silence of a search that lacked the tools to find anything. It is becoming the silence of a serious, capable, multi-method survey that has not found what it is looking for. And that distinction matters. Every year of silence from our current generation of instruments narrows the space of possible explanations. Every negative result from Webb, from FAST, from Breakthrough Listen, is a data point that makes some hypotheses less likely and others more likely. The data is accumulating. The picture is not yet clear, but the picture is being painted. The anthropic shadow, why our own reasoning misleads us. There is a deeper problem with the Fermi Paradox that almost never gets the attention it deserves. Not a candidate solution, a meta-problem. A structural bias in how we reason about the question that corrupts every attempt to think clearly about it. If you don't understand it, every intuition you have about which solution is most likely is systematically biased in a direction that happens to favor our survival, which is exactly the kind of bias evolution would produce in creatures whose ancestors did not survive long enough to have descendants who didn't have it. This is the anthropic shadow, formalized by researchers Anders Sandberg, Milan Cirkovic, and Nick Bostrom in a 2010 paper that deserves far more attention than it receives outside specialist circles. The anthropic shadow rests on a simple and inescapable observation. We exist. We are here. We are observing the universe. This fact is not trivial, and it is not independent of the evidence we are evaluating. Consider a thought experiment. Imagine a universe where catastrophic asteroid impacts capable of sterilizing a planet occur, on average, every 100,000 years, affecting every inhabited world in the galaxy. In that universe, most planets lose their developing civilizations to these impacts. But some planets by chance go 100,000 years, 200,000 years, 300,000 years without the impact that would have ended their biological story. Those are the only planets that develop observers. Those are the only places where intelligences arise that can look back at the historical record and ask, how dangerous has the past been? And when those observers look back, they see a history in which civilization-destroying impacts didn't happen, not because they don't happen, but because the observers only exist in the histories where they didn't happen to them. The observers sample their own history from a biased subset, the subset compatible with their existence. The catastrophes that eliminated other civilizations are invisible to them, not because those catastrophes were rare, but because their victims are not here to report them. This is the anthropic shadow. We are structurally incapable of observing the catastrophes that would have prevented our existence. Our very presence as observers filters our observations in a way that makes the universe appear safer, more life-friendly, and more forgiving than it actually is. We see the history where we survived. We do not and cannot see the histories where we didn't. The implications for the Great Filter are profound. We tend to look at Earth's history, the asteroid that killed the dinosaurs 66 million years ago, the Toba supervolcanic eruption 74,000 years ago that may have reduced the human population to a few thousand, the Cuban Missile Crisis that brought nuclear exchange within minutes, and conclude that we were lucky but not impossibly so. These were close calls, but we made it through. The universe gave us near misses and we survived them. But the anthropic shadow says we cannot trust this intuition. For every civilization that made it through its equivalent of the asteroid, the supervolcano, And the nuclear crisis, the civilization we are part of, there may be thousands of civilizations whose equivalent events did not miss. We don't know about them. We can't observe them. Their absence from the observational record is not evidence that they survived. It is evidence that they are gone. The anthropic shadow also interacts specifically with how we evaluate existential risks in the present moment. We have, so far, survived every existential risk we have faced. Nuclear war did not happen. The great pandemics did not extinguish our species. The asteroid that killed the dinosaurs, not us. Every narrow escape we've had makes the next one seem less likely, survivorship bias at the species level. But every narrow escape might also mean we are one step closer to the escape that doesn't go our way. The anthropic shadow is not a reason for despair. It is a reason for epistemic humility. It is a reason to take the great filter more seriously than our natural inclination to survivorship bias would suggest. It is a reason to invest in the identification and mitigation of existential risks, not because we feel threatened because our own history feels relatively safe, but because the anthropic shadow predicts that our history would feel relatively safe regardless of the actual underlying danger level. The universe, as we observe it, has been hospitable to us so far, but we are observing it from the only vantage point from which observation is possible, the vantage point of having survived. This tells us almost nothing about how hospitable it generally is. The decision we haven't made, how humanity responds to contact. Here is a problem that the Fermi Paradox forces into view that is almost entirely ignored in public discussion. Not a question about what is out there, a question about what we would do if we found it. And the answer, when examined honestly, is, we don't know. We haven't decided. We have no binding framework. We have no governance structure. We are, as a civilization, essentially unprepared for the event we have been searching for. The International Academy of Astronautics SETI Permanent Study Group, in collaboration with the United Nations Office for Outer Space Affairs, has developed a protocol for responding to a detected signal. The protocol runs roughly as follows. The detecting institution notifies the scientific community and international authorities. The detection is independently verified by multiple observatories. A coordinated public announcement is made. A deliberate international process determines the content of any response. The process is transparent, inclusive, and slow. This protocol is not legally binding. It has no enforcement mechanism. It is not embedded in any international treaty. It is a voluntary agreement among a group of researchers who take the question seriously, and whose collective authority to speak for humanity in a contact scenario is approximately zero. If tomorrow morning the Green Bank telescope detected an unmistakable, verified, structured signal from a civilization around a star 40 light-years away, a signal that was confirmed by Parkes and Fast within 24 hours, what would happen? The protocol says, proceed carefully, coordinate internationally, do not respond unilaterally, establish a consensus process. Reality says, every government with a radio transmitter capable of reaching that star system would be under immediate domestic political pressure to do something. Every tech billionaire with a communication satellite array would be making calculations about whether to act independently. Every military establishment on Earth would be instantly treating the detection as a potential security event. Media coverage would be global and immediate. Public pressure would be intense, incoherent, and politically irresistible. The gap between the protocol and the reality is not a small gap. It is the gap between the ideal of rational collective action and the actual behavior of a civilization of 8 billion people, organized into competing nation-states with incommensurable interests. No unified governance structure, no universally accepted authority, and a political class that operates on 2 to 5 year electoral cycles. The search for extraterrestrial intelligence is a project of geological ambition. It might run for centuries before producing a result being conducted by a civilization that struggles to coordinate on projects requiring a decade of sustained commitment. Climate change is a crisis of similar civilizational scope, with similar requirement for global coordination, and 60 years of scientific consensus have not yet produced an adequate response. This is not reassuring context for imagining humanity's management of a first contact event. The question of active SETI deliberate, high-powered broadcasts aimed at specific star systems adds another layer to this governance failure. There is no international law governing whether a nation or private organization can transmit. The Messaging Extraterrestrial Intelligence Community, or METI, has sent several deliberate broadcasts. The Arecibo message in 1974, a teen-written message sent toward Polaris in 2008, several subsequent transmissions toward nearby star systems. None of these were approved by any international body. None underwent any security or risk assessment. They were sent because their organizers had the capability and the inclination. If the dark forest theory is correct, this is exactly the kind of action that a species facing an existential threat should not be taking without global consensus. If the zoo hypothesis is correct, these transmissions may have no consequence because anyone monitoring us is already monitoring us, far more comprehensively than our own broadcasts could indicate. But neither of these conditions has been established, and the broadcasts cannot be recalled. The governance question is not academic. It is a specific, concrete expression of a broader readiness problem. We are building instruments capable of detecting alien life. We are not building the institutional frameworks, the international agreements, the decision-making bodies, or the cultural preparation to handle the discovery. The scientific program and the governance program are running on completely different timescales, in completely different institutions, with completely different levels of funding and political seriousness. The Fermi Paradox is ultimately a question about civilizations, whether they arise, whether they survive, whether they reach each other. And right now, the question of whether our civilization is prepared to handle the discovery it has been searching for is itself a version of the great filter question. Can we coordinate well enough to handle the most consequential event in human history without causing a catastrophe in the process of responding to it? The answer to that question is, at this moment, uncertain. What we broadcast, the signal we have already sent. We have spent this entire exploration focused on what we are listening for. But what we have already transmitted, what we have been broadcasting, without explicit decision or coordinated intent, for over a century deserves equal examination, because it cannot be recalled, and its implications depend entirely on which candidate solution is correct. In 1895, Guglielmo Marconi sent the first radio signals across a meaningful distance on Earth. By the 1920s, commercial radio broadcasting had begun. By the 1940s, television signals had joined the electromagnetic outflow. By the 1950s, military radar installations were adding high-powered directional signals to the leakage. Every radio transmission, every television broadcast, every radar pulse, every cellular signal that has ever been generated on Earth has been spreading outward from our planet at the speed of light ever since. This radio bubble, our electromagnetic signature, now extends approximately 110 light-years in every direction. Within that sphere, any civilization with an appropriately sensitive receiver could, in principle, detect that a technological civilization exists at the center. The signals grow fainter with distance, following the inverse square law, and the earliest broadcasts, the least powerful, the least structured, are at the outer edge of what might be detectable. But the military radars and the deliberate high-powered transmitters produce signals that might be detectable considerably farther. The solar system's bubble of electromagnetic influence from humanity's technology is now visible to a civilization with appropriate technology across a sphere encompassing several thousand star systems. Most of those systems are unoccupied under most candidate solutions, but not all of them need to be. One inhabited system within our radio bubble, even one system within 100 light-years where a civilization exists and has maintained a watch, is enough for our presence to be known. We have also sent deliberate messages. The Arecibo message, transmitted on the 16th of November 1974, was a 210-second broadcast of 1,679 binary digits at a frequency of 2,380 MHz, directed at the globular star cluster M13, approximately 25,000 light-years away. The message was designed by Frank Drake and Carl Sagan and encoded information about the decimal system, the atomic numbers of hydrogen, carbon, nitrogen, oxygen, and phosphorus, the elements of DNA, a representation of the DNA, double helix, a figure of a human being, a representation of our solar system with Earth highlighted, and a representation of the Arecibo telescope itself. M13 is so far away that even if a civilization there received the message tomorrow, the earliest they could respond would be in 51,974 AD. The Arecibo message is not really a communication. It is a statement, a declaration that we are here and that we are capable of asking whether anyone else is. In 2018, the European Space Agency coordinated a transmission called A Simple Response to an Elemental Message, directed toward a star designated GJ273, Luton's star, approximately 12.4 light-years from Earth. The messages were composed collaboratively by artists, musicians, linguists, and scientists. They encoded mathematical relationships, musical structures, and greetings. If a civilization around GJ273 received and responded to them immediately, the reply would arrive in approximately 2042. The Sun itself provides a natural marker. Our industrial civilization has altered Earth's atmosphere in ways that are, in principle, detectable from interstellar distances with appropriately sensitive spectroscopy. Chlorofluorocarbons, CFCs, are industrial molecules that do not occur in nature. Their presence in Earth's atmosphere at the levels they existed before the Montreal Protocol would, to a civilization with web-like instrumentation close enough to observe us, constitute an unambiguous technosignature, not a deliberate signal, an inadvertent chemical fingerprint of industrial activity. The atmospheric chemistry of a civilization. We have been chemically visible since the Industrial Revolution, electromagnetically visible since the early 20th century, deliberately broadcasting since 1974. At no point was any of this decided by a globally representative process. At no point was a risk assessment conducted. At no point did humanity as a whole vote on whether to announce our existence to a universe whose nature and inhabitants we do not understand. This is not a critique. The history of technology doesn't work by global consensus. But it is worth being clear about the situation we are in. We have been broadcasting our presence and our location for over a century, in multiple ways, to a universe we don't understand, guided by no binding governance framework, responding to no coherent strategy, operating under no agreed-upon risk assessment. The message has been sent. It cannot be unsent. What arrives in response will be what arrives. The silence and what it means for the century ahead. The Fermi Paradox, examined carefully, is not a question about alien life. It is a question about civilizations, about what they are, how they arise, whether they survive, and whether the universe produces them in quantities large enough for any one of them to encounter another. Every candidate solution is, in the end, a theory about the dynamics of civilizations over cosmological time. And that makes it directly relevant to the situation we are in right now. Because we are a civilization at a critical juncture, we have the technology to destroy ourselves several times over. We are altering the biosphere in ways whose full consequences we don't yet understand. We are developing artificial intelligence whose long-term relationship to human values and human survival is, at this moment, deeply uncertain. We are approaching what researchers in the existential risk community call a period of civilizational testing, a time when the gap between our capability and our wisdom is at its widest, and when the consequences of navigating that gap poorly are permanent. The Great Filter, if it is ahead of us, is probably operating in exactly this kind of period. Not a single catastrophic event, but a convergence of challenges, technological, environmental, social, political arriving simultaneously and requiring a level of global coordination and institutional wisdom that we may or may not have developed adequately. The filter doesn't have to be a single bullet. It might be a combination of pressures that no civilization has yet found a way to simultaneously survive. The existential risk research community, centered at institutions including Oxford's Future of Humanity Institute, the Cambridge Centre for the Study of Existential Risk, and MIT's Future of Life Institute, takes this seriously. These are not fringe organizations. They include some of the most rigorous, analytically sophisticated researchers in philosophy, physics, computer science, and biology. Their collective assessment is that the probability of civilizational catastrophe in the next century is non-trivial, not certain, not even the most likely outcome, but meaningfully probable in ways that warrant the kind of serious, sustained, global institutional response that a 5% probability of extinction should command if we could think clearly about low-probability, high-consequence events. We mostly can't. Human cognitive architecture is built for near-term, local, personally visible threats. An abstract probability of civilizational collapse in the next 100 years, distributed across multiple causal pathways, involving actors and technologies that don't yet fully exist. This is not the kind of threat our intuitions handle well, and our political and economic institutions were not designed for it either. The Fermi Paradox, in this light, is not a puzzle about astronomy. It is a mirror. It reflects back at us a question about what kind of civilization we are. Whether we are the kind of civilization that passes the filter. Whether we are the kind of civilization that, in 10,000 years, some other species astronomers point their telescopes toward and find that it is still broadcasting. Or whether we are the kind that shows up in the record as a radio bubble that suddenly went quiet sometime in the early 21st century, leaving only the electromagnetic ghost of something that briefly learned to ask questions about the universe before falling silent. The choice is ours in a way that feels almost impossibly freighted. We are the first generation of humans with both the knowledge to understand the stakes and the technology to meaningfully act on them. We know about the Great Filter. We know about the Fermi Paradox. We understand, at least in outline, the shape of the civilizational risk landscape. And we are making decisions, in this decade and the next, about artificial intelligence governance, about nuclear weapons policy, about climate, about biosecurity decisions whose consequences will extend far beyond any individual lifetime, and whose reverberations, good or bad, will shape whether humanity is still here to ask the Fermi question in 1,000 years. The astronomers will keep searching, the instruments will keep improving. The silence may eventually break, in one direction or another. But the most important aspect of the Fermi Paradox is not what it tells us about what's out there, it is what it implies about what we are, about what civilizations are, about how rare and fragile and precious the capacity for asking the question might be. Tonight we walked through the most disturbing question in the history of science, the Fermi Paradox, the screaming contradiction between a universe that should be full of civilization and a sky that has delivered us nothing but silence for 65 years of serious, increasingly sophisticated searching. We walk through the 9 candidate solutions. The rare Earth hypothesis says we are an improbable accident. The conditions that produced Earth, the right star, the right moon, the right tectonics, the right position in the galaxy, the right evolutionary bottlenecks crossed at the right time, are rare enough that complex intelligent life may have arisen only once in the observable universe. The Great Filter says something destroys civilizations before they can reach the stars, and the more life we find elsewhere, the more certain it becomes that the filter is still ahead of us. The Berserker hypothesis says the galaxy is already managed by self-replicating machines built by a civilization that may no longer exist, designed to eliminate new technological entrants before they can become threats. The planetarium hypothesis says our universe is a constructed environment, and we don't find aliens because the simulation we inhabit wasn't designed to include them. The dark forest theory says everyone is hiding. The rational response to knowing other civilizations exist is silence, because revealing yourself in a universe of resource competition and capability asymmetry is suicidal. The transcension hypothesis says advanced civilizations go inward, not outward. They miniaturize into inner computational space, leaving no external footprint, and have no particular interest in announcing their existence to radio frequency scanning newcomers. The zoo hypothesis says we are watched. We are a protected or studied population within a galactic community that has established non-interference protocols, and contact will come when they decide we are ready. The timing hypothesis says we are first. The universe is so young, relative to its total lifespan, that most civilizations haven't developed yet. We are the pioneers. The loneliness is real, but it is temporary on a cosmic scale. And percolation theory says we are in the gap. The mathematics of expansion through an inhomogeneous medium produces bounded clusters of inhabited systems, separated by genuinely empty space. We sit in one of those empty stretches. 9 solutions. 9 different stories about what the universe is and what our place in it is. None of them leaves you exactly as you were before you considered it. But here is what all 9 solutions share, beyond their differences. Every single one of them, without exception, places the question of what happens to our civilization in the next century at the centre of the frame, whether the filter is behind us or ahead of us, whether the galaxy is empty or occupied by hunters, whether we are watched or alone or first. In every version of the story, the decisions our civilization makes in the next 100 years carry consequences that extend across thousands or millions of years of potential future. Every version of the answer makes now matter in a way that is difficult to articulate without it sounding like hyperbole, and yet it isn't. If the great filter is ahead, what we do now determines whether we pass through it or become the next entry in a long list of civilizations that almost made it. If we are first, what we do now writes the founding text of intelligence in the universe. If the dark forest is real, what we do now, whether we continue broadcasting, how we develop our technology, how well we coordinate as a species determines whether we survive long enough to be worth knowing. Even if the planetarium hypothesis is correct and none of it is quite what it appears, the choices we make within the simulation are still the choices we make. They still define us. The astronomer Carl Sagan spent the last decades of his life navigating the tension between his scientific optimism and his genuine belief that the universe was likely full of life, and that we would eventually find it, and his clear-eyed assessment of how precarious our civilization's situation actually was. He was one of the earliest and most vocal advocates for taking nuclear risks seriously. He testified before the United States Senate in 1983 about the concept of nuclear winter, the potential for a large-scale nuclear exchange to produce enough particulate matter in the atmosphere to trigger a global cooling event that would collapse agriculture worldwide and cause mass starvation on a scale dwarfing the direct casualties of the bombs themselves. He wrote novels about contact that grappled honestly with what it might mean, for both parties, for civilizations so different to encounter each other across the void. And toward the end of his life, having spent decades searching and found nothing, having watched the Cold War come to its uneasy resolution, and watched the next generation of threats begin to form, he arrived at a synthesis that still reads as one of the most honest assessments of the human condition ever written. He said in the last public lecture he gave, just months before his death in 1996, that we live in a society absolutely dependent on science and technology, and yet have cleverly arranged things so that almost no one understands science and technology. That is a clear prescription for disaster, and that the only way forward is to make the tools of thinking science, skepticism, the willingness to be wrong, the commitment to evidence, not the property of an elite, but the common inheritance of every person on Earth. He was describing the great filter. He just didn't use the term. He was describing the mechanism by which civilizations might fail to survive their own capability, not through the malevolence of individual actors, but through the structural mismatch between the sophistication of the tools a civilization builds and the wisdom of the civilization wielding them. The Fermi Paradox ultimately is not a question about what's out there. It is a question about what we are and what we are capable of becoming. The silence of the universe is a test not administered by any alien intelligence, not by God, not by any external authority, but by the cold logic of cosmological time and physical law. Every civilization that arises faces the same test. Most have apparently failed it. The universe's examination record is, based on the silence, not encouraging. We know that. We are in the unusual position of a species that has looked honestly at the evidence, understood what it likely implies, and can choose, with that understanding fully in view, how to proceed. That is not nothing. That might be everything. The search continues. James Webb is watching. FAST is listening. The extremely large telescope is being assembled in the Chilean desert, its mirror segments polished to atomic precision in preparation for a sky survey that will dwarf anything that has come before it. Breakthrough Listen's algorithms are sorting through petabytes of radio sky every year, trained on machine learning models designed to recognize structured signals in noise. A new generation of optical SETI telescopes is scanning for nanosecond laser pulses that might be the interstellar equivalent of a flashlight beamed in our direction. The next decade of observation will be unlike any that came before. And somewhere in that data, in the numbers flowing back from instruments pointed at worlds that have never been looked at this carefully before an answer may be forming. The shape of it is not yet clear. It might be a chemical signature that requires 5 more years of Webb observations to confirm. It might be a signal detected at 3, 17 inches the morning by an algorithm that flags it and wakes a researcher who looks at the printout and reaches for a red pen. It might be nothing. A deepening silence that eventually crosses from mystery into near certainty. That too would be an answer. We don't know what the answer is. We don't know what form it will take when it arrives. We don't know whether it will confirm our loneliness or shatter it. We don't know whether what it tells us will be the beginning of the greatest adventure in human history or the most sobering reckoning we have ever faced. But we are asking, with everything we have, with instruments built by hundreds of thousands of engineers and scientists across decades of collaborative effort, with minds trained on the mathematics of probability and the physics of distant light, with a persistence that is, itself, one of the more remarkable things about this species, the refusal to stop asking questions whose answers might be terrifying, because the alternative, not knowing, feels worse. The universe has an answer to Enrico Fermi's 1950 cafeteria question. It exists. The answer is real. It is written in physics and chemistry and the history of every star that has ever burned. We just haven't found it yet. And when we do, it will change everything about how we understand what we are, where we came from, and what, if anything, we are supposed to do next. If tonight left you staring at the ceiling, turning the silence of the universe over in your mind, wondering about the weight of the dark between the stars, that is exactly the right response. That discomfort is not a bug. It is the beginning of thinking seriously about the most important question our species has ever asked. Consider subscribing. We will keep asking the hard questions together. The cosmos is waiting to be known, and so are we.